Hello. How are you all? Let me do this. I'm going to be quite ambitious today with what we're doing. So we're going to be looking at hypothesis testing. Sorry, I'll be one sec. Hello. Look, I managed to get my curtains up. Even though I couldn't get to B&Q to buy the right things, I did manage to find some wall plugs and somehow get it up. It's not really that strong a connection between the wall and the curtains, but I think it'll do for now, and it stops it being too bright coming in, which is really, really good. So we are on week 2 of 4 of finishing the AS spec. We did pure last week, we're doing stats this week, mechanics next week, and then pure the week after, and then all of the AS is done, and we're going to move on to a schedule working with the TT method with past papers, which you're really, really going to enjoy. But for now, let's focus on the stats. So yesterday we talked about binomial distribution, and you had access to those 3 videos for binomial distribution, not 4, because hypothesis testing is what we're going to look at today. And you don't need to worry about normal distribution, that's in the second year. And you don't need to worry about this formula, that's for the second year. And you don't need to worry about doing hypothesis testing with correlation, that's in the second year. But all the rest of it is first year stats. And hypothesis testing, not only is it a decent chunk of marks within the binomial distribution, what you find in the second year is that students are still struggling with hypothesis testing. And the thing is, you need to do hypothesis testing with the normal, which is a bit more complicated, and hypothesis testing with correlation. So it's really important to know which parts of your first year stuff is actually a foundation, and you must get your head around while you're in the first year, and how much of it is sort of fairly standalone, like all this stuff, sampling, that's doesn't even get mentioned in the second year at all, same with data. Whereas lots and lots of what you do in the first year is directly forming a foundation for the second year. So making sure you can do it is super duper important. Hypothesis testing definitely falls into that category. Now, for today, exciting news, we are going to be using Nearpod. So I'm going to write down the code for you. Put it here. Now, ideally, you get Nearpod on your phone, and then you can write on your phone. You could also just get it up as a tab on your desktop, and you could try and write using your mouse, although that is a lot more difficult. And the code that we're going to be using today, the input code, is AIHUX. Okay. You do not need to sign in with a name. You can just put any random letter or number or symbol or anything you like. And also I have turned on hide student names, so it won't show you anyway what you put up. Okay. So if you haven't already got Nearpod, get Nearpod and use AIHUX as the code to get in. Right, timer on. Timer on. That is not a timer. 45 minutes. Go. Right. So most of hypothesis testing is basically a choice. So for each question, you read the question and then you think about what the answer to the choice is. Okay. So in this case, when we're doing the binomial, it's always P equals. P is the probability of success. Don't forget, we did this yesterday looking at the binomial expansion. P, probability of success. What is success? Well, we're going to start every question with the binomial thinking about what X is and describing it properly. So X equals the number of out of how many? Okay. In this case, X is the number of people with red hair out of 20 people. And then this here, this is just a normal binomial question. So what they tend to do is start off with the binomial, then go into a hypothesis test, or start off in the second year with a normal that goes into a hypothesis test. So all of this is what we did yesterday. We're not going to be looking at that. This is just a normal binomial question. Okay, now we look at the hypothesis bit of it. Do we need to change anything about what we're thinking about? X is the number of out of K. Patrick claimed blah, 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 red hair. It's still about red hair. It's definitely still about red hair. So it's going to be the number of people with red hair out of, now look, it's changed. It's no longer 20 people. Patrick claims blah, 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 a sample of 50 people. All right, so now we know how it's distributed. It's binomial, n is 50, and then we have to think about what p is. Now, we're just going to start by filling in on your Nearpod. You should see a H0 and an H1. And what I want you to do is to write next to H0, P equals, and then read this question. And don't forget, none of this bit here is just really a binomial question. It's sort of like an interlude. So this is the question, and then this is the hypothesis test bit. Okay, so what you're looking for in the hypothesis bit or in the information at the front is, what do we think the probability of red hair is? What do we think the probability of getting red hair is going to be? Probability of success. And it's the probability of success according to past data or according to common opinion. Now, in contrast to the null hypothesis, the H0, there's the alternative hypothesis, and you have to choose bigger than, less than, or not equal to. And this is what some random person is claiming. Someone is out there saying, I know we always thought it was this probability of red hair, but I don't think that's true. And they're either saying, I think it's bigger than that, actually, or they're saying, I think it's smaller than that, actually, or they're saying, I don't think it's that. So can you, on your Nearpod, I can see 2 people have done it so far. If you want to change your answers, you can pull it back. So for now, just write down your H0 and your H1, and then I'm going to show you what I can see on my screen. Okay. I'm going to give you 10 more seconds. I'd like everyone to do it if possible. H0 and H1. What is P according to past data, common opinion, probability of red hair? And then there is a person, Patrick, claiming that it is not that. What is Patrick saying? Is Patrick saying it's bigger than that? Is Patrick saying it's smaller than that? Or is Patrick simply saying it's not that? Okay. 5. I've only got 4 on there. Does that, oh, 5. There's 1 more in progress. Okay. I will now reveal your answers. Okay. How do I reveal my answers? Like this. Okay. So we have got, and there's more down here as well. We have got P is 0.05, is categorically agreed by everybody. And then if you have a look at the alternative hypotheses, we've got P is bigger than, P is bigger than, P is not equal to, and this one down here I think says not, that one says equals 0.08. So that's an example of something it might be. So which of these are going to lose marks? Well, it depends. If any of you people are doing OCR, then you've all lost a mark. You've all lost the mark, all of you, if you're doing OCR, because the first mark is for H0, but you also have to say what P is. Now, you don't have to do this for Excel, you don't have to do it for AQA, but OCR, they want you to say P is 0.05, P is the probability of having red hair. They want that written down. They want it's the probability of having red hair. And if you're doing normal distribution, they want to know what mu is. And if you're doing correlation, they want to know what rho is, the parameter of the hypothesis test, okay? So that is OCR people. Now, everybody else, this one here that says P equals 0.08, the correct answer is P is bigger than 0.05. You wouldn't put in P equals. So your options for the alternative hypothesis are bigger than, less than, not equal. That's it. Most people have gone for bigger than 0.05. There's a little mistake on this one, which is that you've got P as 50%, not 5%. Okay, so 50% is 0.5, and actually the chance of having red hair is 5%, which is 0.05. That's this one here. Okay, this one, good point here. You can't use percent. You have to use a decimal. So it can't be 5%. It has to be 0.05, and P is bigger than 0.05. Okay. Now this one here. This one is not correct. Now, the reason for this and what you're looking for in the question is what Patrick is actually saying. So let's go back to the question for a sec and see what Patrick is actually saying, in case we've got any more. Oh, there's the ones up the top as well. So I'll just do a quick scroll. So what is Patrick saying? Let's have a look. Where is Patrick's claim? Patrick claims that people have a probability greater than 5%. Patrick specifically is saying that 5% is wrong because it's too small. It should be bigger than that. So the one that we should have been going for there is bigger than. Okay, so it's all about the claim by the person. That's what tells you which one that you want. So in this case, P equals 0.05, not 5%. P is bigger than 0.05 is the claim. Right, now we have a choice. We have a choice of whether or not to go and find the probability that X is less than or equal to or bigger than or equal to. Okay, less than or bigger than. So the way that we choose this, so I've told you how to choose your alternative hypothesis. It's you have a look what the weird extra person is claiming. Now, how do we choose this? Now, with the binomial expansion, there is always something that we believe to be true. Which is like the average. So what would the average be? What would we expect if we were just doing normal? If this was true, 0.05. So we've got binomial, we're taking 50 people. The chance is 0.05 of them having red hair. How many would we expect to have red hair? This is the mean of a binomial distribution. Second years, you will recognize this formula because you use it when you're approximating a binomial with a normal. The mean of a binomial distribution is n times p. So in this case, 50 times 0.05, 2.5. We are expecting, that's what we're expecting, 2.5 people to have red hair, okay? Now, have a look at what actually happened. This is what actually happened. Actual data from the test, actual data. Okay, have a look at the actual, that's what we're expecting, 2.5. What did we get? 4, right. All you have to think about is 4 weirdly big or weirdly small compared with what we were expecting? So we're expecting 2.5, right? So if we're expecting 2.5 and we get 4, that's quite big, right? If it's weirdly big, then this is what you want to do. You want to do bigger than or equal to. So this is a better way to think about the probability than looking back at your null hypothesis, because what a lot of people are taught is if this is bigger, do bigger. If this is smaller, do smaller. And then they get really, really confused on two-tailed tests about what's going on. So I don't think it's useful to look at this at all. What's more useful is to look at the actual data and to say, well, is 4 unusual because it's big, or is 4 unusual because it's small? And this is the whole point of hypothesis testing. We're trying to work out whether the thing that's happened is so weird that we can, with some confidence, say, H0 is going to get rejected, because we're looking at our actual data and going, do you know what? This is so weird. There's no way we'd get 4 people if that's right, if it's 0.05. No way, it's too weird. So if you've got weirdly big data, you go to the right, and if you've got weirdly small data, you go to the left. And that's compared with what you're expecting, and what you're expecting is the mean, and the mean is n times p. Okay, I would like you now, this is your challenge, to get your calculators. I'm going to give you a blank Nearpod on your phones, like this, if I can make it work. There we go. You've got a blank Nearpod. What I would like you to write down is that we've established that 4 is weirdly big. So I'd like you to get your calculators and work out the probability that x is greater than or equal to 4, and write that on the Nearpod, just that number. We've established that x is binomial, 50, 0.05. The reason that we want bigger than is because 4 is weirdly big. So we're looking for 4 and more. We're looking at the big end of the weirdness. And then just write that down. What is the probability? And if you can remember yesterday, I would like to see on your screen the number line. Binomial, number line. Normal, diagram. Binomial, number line. Normal, diagram. That's the key to not going wrong with this topic. Okay, how many have we got? We've got one answer, which is only to 2 decimal places. Can you do 3 significant figures, maybe? Oh, some more have come. Excellent. Okay. Oh, one person's done the number line. Number line person. Oh, another number line has appeared. It's fantastic. I love your number lines. They're so good. Right. So you should be able to get this on your calculator, right? Everybody should be able to do this. If you've got Nearpod on your phone or on your computer, I'll put the code in again, the Nearpod code, because the more wrong answers we get, the better, because it's in the wrong answers that you learn what the common mistakes are and what not to do. There's no names on there, so it's completely, whatever the word is, anonymous. So it's AIHUX. Okay, let's have a look at the answers that we have got. Here they are. So 0.2395, 0.2395. We've got one wrong answer, which is 0.2396, 0.2395. They both do round to the same thing. 0.2395 will be 0.240. The question doesn't actually say how many significant figures, but you should always do at least 3, okay? At least 3. So I totally agree, and I really like this is my favorite number line, okay? Because what this number line is showing you is that because we want 4 and more, we want to do 1 minus 3 and less. It really makes that clear. So this one here, for example, you can see that's really, really clear from here to here. It's beautifully well done. But this is often a place where little tiny slips happen. So for example, if I make that strictly bigger than 4, this might go wrong here. Or, you know, just little slips. So if you actually just get into the habit of writing out these number lines like this, or like this one is great as well. It just shows exactly what we want and what we don't want. So it allows you to take it off. This one is missing a 0. That's the only, I mean, it doesn't really matter, but binomial, you can always have 0 successes. So there should be a 0 on the end here. But how come we got 0.240? So let's have a look. How many wrong answers have we got here? 204. One wrong answer. What about the rest of you? Is anybody else going to suggest why? Number line, good. I would, on this one, I would put some more as well, because you've put what we do want, but you've made yourself think what we don't want. And if you put them like 2, 3, 4, 5, 6, and then block off what you do want, it helps you to see what it is you don't want. This same method, by the way, really helps when you're doing sigma notation, and it starts at the bottom, finishes at the top, and you're trying to work out, this is for second years, trying to work out how many to do. Okay, so bit too rounding too early, that kind of thing. But yeah, mistakes wise, this looks really, really good. Excellent. So we have now done, what did we get? 0.2396. Okay, so we have done H0, H1. We worked out which of these we wanted to find and we found it. And now we're either going to compare it with alpha or alpha over 2. And this is the first time where anyone cares at all about whether or not it's one tail or two tail. This is the first moment when we care. So what you do is you look back up to whether or not it's one tail or two tail. And if it's one tail, which is to the right or to the left, that's these two, that's one tail, then you compare it with alpha. If it's two tail, which is where you say, I don't know what it is, I don't think it's that, but I don't know what it is, I just don't think it's that, then that you compare with alpha over 2. So two tail is when you say that the P isn't equal to, and one tail is where you say that the P is bigger than or less than. So we're going to do a comparison. So we're going to compare the probability that we got with 5%. And we're going to see which of those is bigger. That one is bigger. I mean, that literally, that's what you need to do. Literally say that one's bigger than that one, right? Now, how do we know whether or not to reject H0? The reason we would reject H0 is because that the result that we get shows that the actual data that we got would happen so rarely, it's so fluky, it's so weird that we're going to reject H0. Now, what is a weird result? The thing that you're looking at here, this number, and this is the important bit, this number here is the chance of it happening by fluke. So the chance of it happening by fluke is 24%. But that's massive. That's not very unlikely, is it? That means that 24% of the time it would happen by fluke anyway. So you're looking for a tiny, tiny, tiny little, oh, yeah, good point. Why did I use 1%? Why did I use 5%? I have no idea. I think because I saw that, because I'm silly. I completely agree with you. It says that the significance level is 1%. It's a one-tail test, so I'm going to compare with 1%. It's still, what's the probability? 0.24. It's huge. Is that right? 0.2395. That's what you all got. It's huge. This is a massive one. It's massive. Way bigger than 1%. So the chance of it happening by fluke is massive. So it probably didn't happen by fluke. So we don't reject H0. Do not reject H0. You only reject H0 if you get a tiny, 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 tiny chance of it happening by fluke. Okay. All right, you ready for the next one? So in this case, we would say 0.2396 is bigger than 0.01. Do not reject H0. It's not small enough. It needs to be tiny. Do not reject H0. There is not sufficient evidence. What's he claiming? There is not sufficient evidence that Redmond people have a probability greater than 5% of having red hair. That would be your 3 parts of your conclusion. Okay, I'm going to put a new Nearpod on your phone, and it is going to be for the next question. You don't find the probability that it's equal to 4 because, and this is important, what you're trying to do is you're trying to work out how weird the result is. Okay, so let me just pick a random page. Here is the things that could happen. Like this. Okay. Now, this one is obviously the mean. This one is the most likely. So let's say that I get the thing that is most likely if we're right that this is P. If this is correct, H0 is correct. H0 says that P is whatever, and that's actually true. Then the most likely thing that's going to happen in my test when I do my actual data is that I will get N times P. That's the most likely thing. Now, what is the chance of getting the most likely thing? Teeny. If I have a coin and I toss it 100 times, then what I would expect to happen is to get 50 heads and 50 tails. Do you think I will get exactly 50 heads and 50 tails? Probably not. This height here, this whole area adds up to 1. Add up, add up, add up, add up, add up, 1. That doesn't mean that this is high, because you could have N is 1,000, couldn't you? And the most high one could still be really, really, really unlikely. That's not what we're calculating. We're not saying how likely is it to get 4. What we want to work out is how extreme is 4, not how likely is 4. So how likely is 4 would be the probability that X is 4. We're not asking that question. How extremely weird? How extreme is 4? That's what we're asking. It's how far down the ends is 4. So if 4 is there, then it's really, really unlikely. And if 4 is here, then it's really, really unlikely. So what you measure, the way to measure that is to measure the probability that it's bigger than or equal to 4. Because the further to the right, the smaller that is. And that's what we want to know. We want to know how far to the right is the result of the survey. How far away from what we expect is it? Now, if you measure the likelihood of getting 4, you're not finding out how far away you are from the mean. You want to know how far away you are from the mean. And the way to do that is to calculate how much area is still going after that point. That's what a hypothesis test measures. It finds out this probability is how many times, or what proportion, how much would it happen by fluke. So it is possible that this P is correct, and then I do a sample. Like, I could have a fair coin and I could toss it and toss it and toss it and toss it, get 99 heads. I could. Doesn't mean anything. That definitely could happen. Definitely. So what we're trying to find out is how far down the ends have I gone? How far into unlikely have I wandered? And that's why we find always the probability, oops, that's correlation, don't worry about that. Always we find less than or equal to or bigger than or equal to. That's your only choice, always. Okay, next one. So I'm going to give you 15 seconds to read it, and then on your phone, write in H0 and H1. And I'd like as many people as possible to do this, please, so that we can see some wrong answers as well as some right answers, just to see like what sort of thing goes wrong. We're not doing A, by the way, we're not doing this. This is where they just do the normal binomially bit. And then this is where they're doing the hypothesis test. So H0 is going to be P equals, and this is the generally held belief, the like past data or common belief. And then this one, you have to see what somebody is claiming. There is somebody who is saying in this case, it's a radio company, not a person. They're making a claim. Okay, let's have a look. How many have we got? We've got only one at the moment. Hang on a minute. Where has it gone? There. Hope I didn't kick you all out just then. Okay, so, okay, good. We've got a nice variety now. Does anybody want to add another one on? Well, you can add them while it's on the screen, to be honest. Okay, here we go. So, bit of debate about what P equals, and this one here, you must say P equals for H naught. H naught has to be P equals. We'll come back to critical regions in a minute. Has to be P equals. P equals 0.25, P equals 0.1, P equals 0.25. So why is it 0.25 and not 0.02 and not 0.01? Why is it 0.025? Well, if you have a look at the actual, you need to read it really carefully. Sometimes it isn't obvious what the P is, the original P, the thing that people think it is. In this case, it's because it says the proportion of houses unable to receive radio is 25%. That's fact. That's stated as like, that's what people believe. So that means that H naught is that P equals 0.25. Okay, what about the claim? So who's claiming what? There's the radio company, and they're claiming that this will reduce the proportion of houses, reduce, get smaller. They're making a very specific claim that it's going to get smaller. So this one is not correct. This one is where the radio company is just saying, I don't think it is a quarter. And that's all they're saying. This one is not correct because your only options for H1 are P is bigger than 0.25, P is less than 0.25, or P is not 0.25. They're your only options. This one for not equals as well. And it's about that claim. You have to look at what the person is saying, because in this case, they're not saying, I don't think it is 25%. They're saying, I think it's less. I think it's reduced. This is correct. P equals 0.25. P is less than 0.25. Perfect. Okay, good. This is the correct one. Okay, now I'm going to give you, this is very important. This is not correct. Whoever did this, thank you, because this is really, really important. The alternative hypothesis can't be partly the same as the null hypothesis. So if the alternative hypothesis is less than or equal to, then that's wrong. It has to be literally not equal, bigger, smaller. They're your only options. It cannot be a non-strict inequality. Good. See, it's so, I can't teach as anywhere near as well if I don't have wrong answers. The wrong answers are what absolutely does it in terms of helping you to understand. Okay, next I'm going to give you a blank one, and I would like you to write down what probability we are going to find in this question. Okay, so we've decided what H0 and H1 are. And now we're choosing between the probability that X is less than or equal to, or the probability that X is bigger than or equal to. And I want you to write down what number goes there. So you don't have to calculate it. Just write down this or this. I'm going to give you 6 seconds. Is it weirdly big? In which case go to the right. Or is it weirdly small? In which case go to the left. And if you don't know, guess. It's 50-50 guess, isn't it? Just pick one. 4, 3, 2, 1. Look at this. Let me show you what I can see. Literally. Oh, they've appeared. They've appeared. Good. Okay, so we've got 1, 2, yes, but what number goes in here? So these two people, what number goes there? Can you add in a number here, add in a number here, add in a number here, like this? So is it 1? If it's weirdly small, if 1 is weirdly small, if that's the result that they got, then you need to go less than or equal to, because you're seeing how far down it is to the left, okay? Now, 4 is what the result was on the previous one. On this one, the number of houses not getting radios was 1, not getting transmission, yeah? So if 1 is, look at this, look at all the different ones we're getting here. This is where the problem is, isn't it? It's knowing what it is you need to find the probability of. Let me go back to the question for 1 sec, and then we'll have a look, and you can change these as we go. Right. What you're doing at this stage is you are choosing between less than or equal to or bigger than or equal to. And you're choosing based on whether this number here is weirdly small or weirdly big. If this number, which is the result of the survey, that's what this is. We do a survey with some people and then we get the result. So if the actual real life result is weirdly small, then you go less than or equal to. And if the real life result is weirdly big, then you go bigger than or equal to. Now, how do we know what we were expecting to happen? We talk about what X is and how it's distributed. X is the number of X is the number of unable to receive radio, number of houses with no radio, out of 15. It's binomial 15, 0.25, and the 0.25 is the P that we chose at the beginning. So what are we expecting? We're expecting the mean would be 15 times 0.25. So we're expecting 3.75 houses. That's what we're expecting, 3.75 houses. How many houses actually, from the 15, how many houses actually didn't get any radio signal? One house. One house. So this number here is 1, because that is the actual thing that you actually found, actual data. It's how actually many. So you need to compare with 1, not with anything else. You can use the rubber and change your answers. And then what you need to decide is, am I going to find the probability that it's less than or equal to 1 because 1 is really small and I'm finding out how small? Or am I going to find the probability that X is bigger than or equal to 1 because 1 is weirdly big and I'm going to the right and seeing how far to the right it is? Okay, let's have a look at your answers now. Good. So we've all got 1 because that was the result, but we've still got some disagreement about whether it's less than or equal to or bigger than or equal to. Now we're expecting the normal thing. If there's 15 trials and 0.25 chance of success, the normal thing would be 3.75. 1 is really, really small. So it's less than or equal to. Perfect. Less than or equal to. Absolutely perfect. Okay, super fast so that we can go on to the next one. Grab your calculator and we will just have a race. You can on the screen. So what is the probability that it is less than or equal to 1? Don't forget that our distribution was binomial. N is 15 because there are 15 houses that they looked at. And the probability, we think, P is 0.25. So you're going into your calculator, you're doing the probability that it's less than or equal to 1. Oh, sorry, people at the top, I didn't show your answers. We've got 0.08. Do we agree with that? It's gone. Okay, it's back. Excellent. Anybody want to put up a probability that agrees with that or doesn't agree with that? You should be in your calculator, binomial CD, 15 for N, 0.25 for P, and then 1 for X, less than or equal to 1. Okay, I'm going with 0.08 because I think it's correct. Yay. Okay, let me give you all a new screen and I'm going to remove so you can't see each other's for a minute. It is less than or equal to 0, what was it? 0.08. 0.08. Probability that x is less than or equal to 1 equals 0.08. Right. What I'd like you to put on your screen now is the comparison with alpha or not alpha, alpha or alpha over 2. So it's going to say one of these, and then put reject H0 or do not reject H0. So I want to see the comparison and then do or do not reject H0. So you're looking in the question, what is the significance level? What am I allowed to count as weird? That's what the significance level is. If the significance level is 10%, then anything smaller than 10% is considered really weird. If the significance is 0.5%, then only things less than 0.5% are considered weird enough. That's what the significance level is. How weird are we going to go? Okay, so I'm looking for a comparison and then do or do not reject H0. I'd like a few more before I put it up, just so that we can compare different answers. And there's a couple of you've got that probability right, but can you write yes or no to rejecting H0? You can write yes or no if you want. Are we going to reject H0? Okay, great. So, something to say about this one. Oh, wait, why is it not showing you? Anyway, this one is that it's never really about accepting H1. This is a really subtle point, but really what we do in hypothesis testing is that we find evidence to suggest not right, because if H0 was right, then how come we got this really, really weird result? So we find evidence that H0 is incorrect, and it's only evidence, it's not a fact. So we reject or do not reject H0. It's not really about accepting or not accepting H1. It's about rejecting or not rejecting H0, okay? So the comparison that we would make here, where are you? I'm just going to refresh this page because I can see that you've got more answers than this up, but they've disappeared. I can see them on the other screen. I can see 3 or 4, 5 even. No, you do not need to look on a table, no. You can get the information from a table, but it's way easier to get the information from a calculator. Okay, so while this refreshes itself, I'll tell you what we should have. We should have that 0.08 is less than 0.1, and you need to actually say 0.1. So the person who's writing in red, you've put 0.08 less than alpha. You don't put an alpha there. You have to say what alpha is. So change your alpha. And also the person who has written tick reject H0, you've put less than alpha, and you need to put less than 0.1 to show what your actual alpha is. The rest of them, yeah, and there's another person that's done that. Actually, 3 people did less than alpha, and you have to actually say what the alpha is, otherwise it's not a comparison. Good, okay, then reject H0. Reject H0. This is really weird, right? It says my internet connection is unstable on my Mac, but I've got a Mac there that's got the internet's fine. So I don't understand why the internet is. So where does 0.1 come from? 0.1 is the significance level of the test, and it's set within the test. So the significance level is how weird can I be? What is weird enough to reject H0? So it's always set by the questioner. In this case, it would be 10% is weird. Anything below 10%. Yep, so alpha is 0.1 because of that 10%. Yeah. I do not know why this Nearpod is not letting me see it because I can see it on the other screen. But anyway, let's go on to the next one. Let's do this one a little bit faster. Okay, right. This one is a bit more tricky because of the way it's been phrased. So let's see if we can apply our understanding to this situation. Okay. So they tell us H0. H0 is P equals 0.3. So that means that we think the probability is 30%. X is the number of somethings, successes, out of 20. And X is distributed binomially and N is 20. And apparently we think P is 0.3. Okay. Now, this is a nice example of the alternative hypothesis not equal to. So the way that we would phrase this is Patrick thinks that the common belief is wrong. Patrick thinks that the company is incorrect. The company thinks that the probability is 0.3. Patrick says that the company is wrong. That's what that is. Not Patrick says that there's more or there's less. He just thinks it's wrong. So this is the two-tailed test. But until we get right down here, we don't care that it's two-tailed. When we get right down here, this is irrelevant. This bit, one-tailed, two-tailed, not relevant. This bit, relevant. So we're using P not equal to for this one. Okay. We've got 5% level of significance. So that's our alpha. Alpha is 5%. Or alpha over 2 is 2.5%. And the probability of rejecting each tail, so we're at both ends, because I'm not specifically saying weirdly big or weirdly small, it can be both. Find the critical region. Now, this is the one I wanted to get to, because this is the other side of the coin. This is where instead of me doing a test and getting actual data, an actual result from an actual test, and then finding out how weird it is, in this case, it's the other way around. So in this case, I'm saying, well, how weird would I need to go? What would count as being sufficiently weird? Okay, so here's the picture. How low would I have to go for it to be weird? So what you do is you get your calculator. What would we expect? Well, we would expect 20 times 0.3, n times p. We would expect 6. So let's try 2. You grab your calculator, you literally just try it. What's the probability? So you go into your menu 7, and you go binomial CD, variable. This is all what we did yesterday. X is, let's try 2. Let's see how big this area here is. How weird is this? How far towards the left-hand end is this? N is 20, P is 0.3. Probability is 0.03, that's too big. 0.035. 5. I'm trying to get as close to 2.5 as possible. Let's change it. Let's go back one and then say, change the X to a 1. Oh, now it's weenie. Oh, no. All right. All right. So probability X is less than or equal to 1 is 7.64 times 10 to the minus 3. Now, only one of those is less than 2.5. We're comparing with 2.5 because it was a two-tailed test. It had both directions. It wasn't specifically saying bigger or specifically saying smaller. But in this question, instead of saying, I need you to be smaller than 2.5, it says as close as possible. And don't forget, the significance level is chosen by the person setting the test. It's not like a mathematical thing. It's just how weird do you want to be before rejecting H0? Now, in this case, the one out of these which is closer to 2.5% is actually the first one. This one. So this is going to be our critical region at that end. These are the things that are sufficiently weird that would allow us to reject H0. Now we go to the other end. Well, it's out of 20, 19, how weird. I think maybe 10 is quite weird. So we'd get the calculator and we go, X is 10, N is 20, P is 0.3. And I find out that this area here is, oh, I don't find out anything about that area, do I? I find the area to the left because that's what it always gives me. So be very, very careful at this end. What I've got from my calculator is this. This, because I put in 10, don't forget, that bit there is 0.9828. And the 10 is now to the left. So what I've actually found there is the probability that X is greater than or equal to 11. So if this comes out really close to 0.75, 0.975, sorry, then it would mean the area to the right is close to 2.5, which is what I want. But you have to be so careful with what you put in here versus what is a critical value. So I'm going to go one higher. I'm going to go all the way up to 11. I'm going to find the probability that X is less than or equal to 11, which is not equal to, which is 11, 20, 0.3. There. Now, which of those is closer? I need the right-hand bit to be as close as possible to 2.5. So I need the left-hand bit to be as close as possible to 0.975. This one is closer to 0.975. What if I go down one? So I'm literally just testing out these numbers. X is 9, N is 20, P is 0.3. That comes out to be 0.9520. And I want 975. So you have to think which of these is closer to 0.975. Press the wrong buttons on my calculator. Which one is closer? 9.7. I think this one's closer. So that means that's the cutoff there, and this is my critical region. So my critical region is 0, 1, 2, 11, 12, all the way up to 20. That's the critical region. And the critical region is the ones which, if I got them when I did my actual test,